We talk about topology. We talk about topology. Uh, Topology, the Greek word topos means locations and logy means study. The motivation behind it, uh, before topology, Euclidean geometry was defined, and most of the standard objects are almost defined, and we know some of the properties of there. In such case, there is a fact that some of the figure or geometrical object or mathematical object are not similar in shape, but their property may be same in some cases, and some of the properties are different. As for example, this is a circle and this is a square. It has an inner part and this is outer part. Both are defined on plane. This is inner part, outer part. You can fix up a center that is equal to the every perimeter has same distance, and it is also defined a center that can be symmetric versions you can define on it, and it may be to our similar area if you can do that in some conditions that the radius are equal on it, then in such cases it may be possible to define of same areas. These two one-dimensional objects, geometric objects, have some similar properties, but they have some different properties. From this intuition, we generalize it for study. Then we get that it can be defined by mathematically. So topology. So topology is concerned on geometric object that can be mathematical defined. Yes. It allows continuous deformations. But does not allow opening holes of the figure, closing hole of the figure, gluing, tearing, and self-intersections. In continuous deformations, what kind of deformations? Stretching, bending, crumpling, and twisting. I have tried to show in some deformations, but it may have some other deformation, but it must be a continuous deformation under such conditions, or provided some conditions that has no loss of the figure and no loss of the area. Stretching, and to talk it, stretching. Stretching we know about from the word, like a rod, we stretch from the both side that it make it like so large. So this figure converted into like this. This is stretching, and bending. Bending also like this is a rod like this. It may be formed like this. This is a bending. Crumpling. Crumpling is this is a piece of paper. You make it like this. You make it like this without any cutting. This is crumpling. And twisting, you may know that this is a rod. You give it to pressure on fixed in, and this side make it like this, then it will be made like this. If you will show in a their pressure will be like this. This is twisting. These continuous deformations can be shown. Yes. Continuous deformations are considered on homeomorphism and homotopy. We will discuss in later, but it is bijective continuous. And homotopy, we know, we study that fixed this circle like this point and make like this and this. We'll study it later. Such deformations. And when topology, we already talk about that topology define on geometric objects, and I told you that it can be expressed mathematical define. So the deformations defining are the deformations, continuous deformation of surfaces. In topological phase, it has not very old topic. It is very new topics. Some of the result of topology has been used more than 200 years, but it has more developed in 20th century. So I can say that in Euclidean phase, the topology is used, but we are not realize it that this can be defined as a generalization like as topology. So in one of the example, we may know that in the bachelor course that the metric phase, it's a topological space defined on uh, metric or any distance any distances. So metric space uh, metric space are mostly defined on Euclidean space. So topology was already involved in it. So we now go to the next point. We will try to define topology. Actually, before starting this, we will say topology is defined on a set X. In such cases, it is defined that X is a non-empty set. So non-empty is required to avoid trivial case. And topological property is invariant under such continuous deformations. This is topological property. Example: topological dimension. In topological dimension, we can distinguish between a circle and a line. We will study on topological dimension in next lectures. And another topological property is compactness. We already know about it, and connectedness. There are a lot of topological properties like this. It helps to define and distinguish some of the surface, line, and their relations, and some of the properties. That's all. Any kind of continuity can be defined on the surfaces of the topological space. Now first want to describe the topological space. What is a topology? First, one through definitions. The definition of topology: let X be a set and X be a power set. You may know about it already. Power set. A family or collections of sets this is defined tau. This is a family or collection of sets. Whose collections? Na of some subsets of power set of X. Power set of X. What do we get? Now, we already know about set. We consider X be a set and we define Px be a power set on X. And we take a family or collection of sets tau of some subsets of power set X. Then tau is a topology. Topology on the set X if it satisfied some axioms defining on open sets. The axioms are phi and X belongs to tau. Phi is a null set. X is the whole set. Tau is collections of family. This. Number 2. The union of any collections of members of tau again belongs to tau. So tau is closed under arbitrary unions The union of any collections of members or collections of sets of tau again belongs to tau. And the finite, the intersection of finite collections of members of tau is again a member of tau. What is this? Tau is closed under finite intersection. If the three axioms are satisfied, then tau is called a topology. This is the definitions of topology. Now, the tau is a topology on set X, and X tau is a topological space. In the definitions of open set in topology is different. Open set. The members of tau on X are called open sets if these sets are belongs to tau. Closed set a subset A of a topological space X tau is called closed set if x uh, minus a set inclusions, it is not a minus in subtraction minus, belongs to tau. Open set plus closed set, this is called clopen set. That's all. It satisfies both of the properties. Some of the issue arises, this is not more such important, that the tau is a topological structure. In some cases, some of the players write down that X is a topological space and X is a topology. It is just make it a convenience, nothing else. That's very simple, that X is a topological space. But it really we have studied that X tau is a topological space. This is the most convenient thing to realize it and understand it. But in some cases, for general discussions, we just write down T is a topological space, X is a topological space. We can write it, but it is no such a great fact. I think that it make it convenience. That's all. It make it a level of understanding in the article or publishing journal. They will realize it that it has a structure. So it's not a problem and this is not an issue. But when we are starting the study of these topics, we'll write down X tau always. Example of clopen sets. X tau is a topology. Kalpas. Phi null set and whole set belongs to tau. These two sets always clopen sets. Satisfy the property of the clopen set or definition are satisfied, so it is a clopen sets. We go to the example of topology. First, let X is a set A, B, C are the elements of the set, and tau 1 is equal to phi comma x, tau 2 is equal to phi comma x comma a, tau 3 to phi comma x comma a b ab, tau 4 is equal to phi x c bc. From where we get this? We get this power set of x. Power set of x, we get this such collections, and we define that tau 1 is a topology. This is taken only two elements, and tau t is this 3 subset, tau 3 is this 5 subset, and tau 4 is this 4 subset. Then if we will check it the 3 axiom of the definition of the topology, then tau 1, tau 2, tau 3 and tau 4 are topology defined on X. In similar manner, to use the definitions of power set of a set, you can construct a topological set. You can define more other topological pairs and topology. Sorry, yes, we are in the same example. Tau n is equal to number of elements of the topology tau on X. So for case of tau 1, number of elements will be 1, tau 2 will be 4, tau 3 will be 29, tau 4 I have calculated it already, but if you will calculate it from the power set, you can get this result that it's maybe possible to find out such topologies. Go to tau 6 equal to 209527 and tau 7 is equal to 9535421. That's all number of topologies. We come to next examples. In some case you can see that phi and x only. This is a topological pair. This topological pair is not such a important. This is a trivial topological path, logical path, but it is called in different name. This is very important. It is called indiscrete topology. This is called indiscrete topology on X. We'll come to another point. X non-empty set. Okay, P of X or P of X. This is power set of X. If it will be the equal to tau. Actually, we are discussing that tau is a subset of P of X. If tau is equal to P of X, power set of X, what will happen? This is discrete topology on X. Discrete topology, and this is indiscrete topology. This is the two definition we have got. Next, suppose for any arbitrary subset A of an infinite set X, the define of topology is like that, equal to B subset of X is subset of B include phi is a topology on X. This topology has a specific name. The name is A inclusions topology on X. The infinite case, the infinite number of distinct different topology can be defined on an infinite set. Yes. Next, let X be a infinite set. And tau subset of power set consists of all phi and those subset of X. Which kind of subset? Now whose complements in X are finite. sets. Then tau is a topology on X. This topology is called co-finite topology. Or the topology of finite complement on X. The next, X uncountable infinite set. Okay, tau consists of phi and all those subsets of X whose complements are countable subsets. This tau is also a topology. It satisfies the three axioms of the definition of the topology. This topology tau is called co-countable topology, or the topology of countable complement on X. Next, the description of all other examples are in many books, mostly monkeys. The examples are mostly defined very clearly. I will not go interest on it because it's a verify is needed, and it's very easy. Just think it the set and define that the three axioms are satisfied. That's all. The co-countable or co-finite topology on a set X becomes a discrete topology when co-countable topology will be the discrete topology when X is a countable set, and it will be a discrete topology for case of co-finite topology when it is a finite set. That's all. The next is a very important. X is a set. This has only two elements, A and B, and we define the topology tau s is has a specific name ys, x phi and a. This is a topology. Is a topology on X. We discussed in the first example that this is a topology on X. So X comma tau s topological space. This topology has a Basal name. This is Sierpinski space, Sierpinski line, Sergi-Frey line. They are mostly important in topology. In such topology, in some examples are most valuable, but in examinations there are some of the conditions that which such conditions are satisfied on in which topology. So these are most useful in some examples, when they ask some crucial examples. Such examples are very crucial in such cases. X is a set. So element A, B, and C. Tau 1 is a topology x, phi, b. And tau 3 is equal to phi, x, c. Yes. The most important question is, the union of two topology is a topology? No, it's not a topology. It's not a topology. If you will see this will be phi x, b and c, but it will not satisfy the three axiom of a topology on set X. So we get the information that union of two topology may not be a topology, but in some cases it may happens. Now we discuss that topology tau alpha belongs to a index set. Is a family of topological set X, non-empty sets must be, then the topology tau is arbitrary intersections of the index set tau of alpha is a topology on X. My proof is very obvious. You can find it. This also exercise in markers. Next, we will comes to the another point on topology. This is finer and coarser of topology. Tau 1 is a topology and tau 2 is a topology. I think it's defined on a set X. On X. Stronger or finer or larger. Another is weaker or coarser or smaller. Any name can be used. We will see to the definitions. How can we will get that this one is stronger, this one is smaller, this one is coarser, or this one is finer? How can I find it? Just example, tau 1 and is a subset of tau 2, or tau 2 is a subset of tau 1. It will be defined according to your definitions. But it will not be happen always. In such cases, this property is called the comparable properties of topology. comparable whatever topology. If not happen, you are obliged to write this. This is equal to this and this. This meaning is that will not satisfy these two. If both are not satisfied, then this will be written like this. If these conditions are satisfied on a defined set X, then we will say this is a stronger topology and this is a weaker topology. Some of the questions arise that in discrete topology and discrete topology, which one will be the stronger topology and which one is the weaker topology? It's very obvious that indiscrete topology is the weakest topology and discrete topology will be the stronger topology. In this case, on the discussion on it. An uncountably infinite set for co-finite topology is strictly weaker than the co-countable topology. The topology are weaker and stronger, has some property that define it later. Then we will realize it when we discuss about the topology in operator theory. It is very important to see the weaker topology and stronger topology. It is necessary to come into the point of the advanced topological discussion. Then we will find out the importance of these topics, but this topic is very important when we will talk about like as examples limit points of a set, then this limit point of the weaker topology and limit point of the stronger topology has a great importance and difference between it. In such cases, it's very important. So finite topology and coarser topology is important things in discussions of a limit point in such cases of operator theory. Up to this discussion, we learn the motivation of topology. We get the definition of the topology and open set, closed sets, and example of topologies and finer and coarser topology. That's all.